Hi there. In today's lab, your first lab for Plant Science 2, you're sort of looking at a real rough assessment of soil characteristics. We're going to say texture analysis. So as a preparation for the lab, I want to go over some of the what we call physical properties of soil. So structure, density, porosity, and color and texture. And texture is the one that today's lab will focus on. Um, Looking at how it feels, how it forms, and we use that as just a real rough initial guide to characterize soil. So there's our soil snowman yet again, but yeah. Anyways, so starting off with, if you grab a handful of a particular soil, you want to see how's that soil feel. Is it smooth? Is it gritty? Is it sticky? What's the overall feel of the soil? If it's gritty, then we have an idea that there's sand in that soil. If it's very smooth and sticky, it's going to have clay content. Um, as far as structure, the structure is relates to the individual particles, right? So soil is an amalgam of lots of different types of sizes and ingredients, and how they come together also influences the structure. So do they form hard chunks that are mixed in between soft chunks? Is it very uniform? That kind of thing. And when it comes to horticulture and agriculture, those properties come into play when you're trying to figure out how to work the soil and what's needed to amend it so that you can grow vegetables, for example, uh, with decent germination and success. So the density is related to its ability to compact. I got a picture here of a tire leaving some tread prints in some sand. Um, just about any sand will leave compression marks, but how stable are those compressions? Are they ones that are difficult to break up, or do they crumble easily? So the density of the soil plays a really big role in that. As far as equipment compacting it, or the ability of equipment to get into it for seeding or planting, it also impacts things like drainage and oxygen. Um, Porosity is probably the biggest one when it comes to drainage and oxygen. And as you will begin to see, everything kind of is interplaying, right? Um, these cross sections of soil here are showing clay, silt, and sand, and the same volume of water being deposited. And the clay has it sort of pooling on the surface. The silt has it sort of wicking down, and the sand it penetrates very deeply, rapidly. So in terms of porosity, sand has the highest porosity, meaning the water is able to drain readily and deeply, where clay has the lowest porosity. Um, we have another lab coming up. I think it's the week after. Next week we're looking at micropores and macropores, so we'll discuss that. Our next class, I mean, which would be what, Thursday. So so porosity refers to the size and quantity of pores or spaces in the soil. Color is another interesting property, right? The color gives us an indication of what makes up the soil. Is it dark brown? That means it's got high organic content. If it's light yellow or red, it may have oxidized or hydrated iron in it, which is an indication of maybe poor drainage. And then lastly, we look at separates. In today's lab, another exercise is taking a soil sample and mixing it into a volume of water and then putting it into a tall glass jam jar or whatever in your case at home, and letting the soil settle into the different layers, be it clay, silt, and sand. The coarsest layers settle first, followed by the silt, and then the clay. And by measuring the total height and then the percentage that each layer represents, we can use that information to sort of classify the soil, whether it's a sandy loam or whatnot, and we'll use the texture triangle for that. Um, as a whole, though, when all those individual elements are mixed into a soil, they can clump and form what we call aggregates. Here's a cross section of the different types of particles that you would come across in soil. Clay being the smallest, less than 0.002 millimeters in size, and it's not visible under a microscope. So basically, in the sort of geological scale of soil starting as a solid rock and then eroding and wearing and getting smaller and smaller and smaller, clay is the final stage of soil evolution before elements are fully solubilized and washed away completely. In Niagara, we have a lot of clay soils. This is one of the reasons why grapes seem to do fairly well in some areas, not just microclimate, but also the soil. Clay has lots of nutrients. Now, clay soils are not great for fruit trees, so those tend to be in the more sandy soil areas. But there's definitely a lot of clay in the Niagara area. Clay under a microscope, a scanning electron microscope, gives you a lot of insight into the structure, and you'll see these sheets, these thin wafers. They're like stacks of paper piled on each other. This is what gives clay its unique properties. Clay is a phenomenal resource for plants to store water and nutrients. The downside, of course, is with this tightly packed structure is there's not a lot of room for oxygen. So here we have a picture of clay particles that have different elements stuck to the surface. Later in the course, we'll discuss the chemical properties involved in that and how soils can store nutrients. But essentially, roots reach out and will extract nutrients from those particles. And clay has the highest nutrient content of all the soil elements. Obviously, everything in soil science is a compromise. And you could say, well, then I should just grow in clay. But yes, you'd have lots of nutrients, but you don't have oxygen, you don't have a place for water to escape. So obviously the ideal soil has a percentage of clay and a percentage of sand and a percentage of silt. And that's where in the middle of the texture triangle is that sort of classic loam, which is a balance of all the different particles. Silt, which is exactly what you probably thought it was, is often what comes out in rivers. It's sort of the last stages before soil and rock has eroded to the clay. It's the next size up. And in rivers, the rocks that are tumbling and washing over each other knock little bits off, and the smaller particles will fill up the river in what we call silt. In estuaries where the water slows down, the silt settles and starts to fill the bottom of the river. So silt is still a very small particle, anywhere from 0.05 down to close to the dimensions of clay. It is visible, so you can see the individual particles under a regular microscope, unlike clay. This is a scanning electron microscope view of silt. So you can see the particles are starting to look kind of sheet-like, but they're not as defined as individual sheets as clay is. They're still kind of clumpy bits. Then there's sand. Sand is sort of the last fine particulate before we get into things like rocks and gravel. Sand, we're all familiar with it. A lot of the sand we go to at the beach is quartz or silicate rock, but sand is really just a dimension that can be found with lots of different rock types. You can make sand from limestone, but it's highly soluble and will eventually dissolve. And you can make rocks from granite, and you can make rocks from quartz. So now often other minerals will dissolve or break down sooner from granite, which would leave much more quartz behind as the sand is aged. So it's not uncommon to see more quartz in sand than you would normally have found in the original rock, because the other parts of the rock have since dissolved. So clay, to summarize, particles are not visible under a microscope. It is probably the most important component of soil because of its ability to store nutrients and a storehouse for water. It is also what imparts stickiness to soil. The clay is the part that makes soil hold its shape. So later in the lab, when you do your uh, making ribbons and rolling soil in your palm, looking at how sticky it is will help you sort of to give a qualitative assessment of how much clay is in that soil. Um, so, whoops. Silt, on the other hand, which is visible under a microscope, it's decent small spaces, so you have a little more drainage. It's got moderate water holding capacity. Again, it's sort of halfway between sand and clay. It's fairly fine to the touch. It will stay suspended in water for um, maybe anywhere from a few minutes to an hour, where clay takes many, many hours to settle. Um, Sand, which is visible to the naked eye, is usually fairly large, rounded particles, large pores, so excellent drainage, but a small surface area, which means it doesn't have a lot of water holding capacity and does not store nutrients, but it is good for aeration. So certain crops that like good drainage do very well in sandy soils. It does erode easily, right? So it's not a very stable soil. It doesn't have that clay to bind it, so it will wash away more quickly. It's not always ideal, though. As far as aggregates, that's these chunks. They can be bound together with all kinds of organic molecules as well, right? Um, so organic fertilizers or dying organic matter will also bind up those soil particulates into aggregates. Um, in more mineral-based soils, we often see things like iron oxide, silica, clay, or calcium carbonates will also bind up soil into chunks. As far as aggregates go, there's two groups. There's what we call PEDs, which are aggregates that form naturally, and then there are clods, which is from tractors tilling the ground. That's two fancy little terms there. So PEDs are naturally formed aggregates, and clods are aggregates formed through a human activity, right? A plow going down the road, or you take a shovel and you dig up soil. So aggregates, in terms of plant growth, we need something that will take water and store it, but not collapse. We need a certain amount of structure, but we also need some porosity. We need a variety of particle sizes so that we get that structure in the soil that gives us air, stores nutrients, also holds water, that balance. So when we're looking at pores, we're talking about both air storage and water storage. And large pores are what we call macropores, and small pores are micropores. And in the video that is linked in today's lab folder, I have a couple of 3 different size screens that I fill with water and hold up, and you can see the water drain. And the idea is that the coarse screen, the water is able to span the gaps between the wires because of surface tension. But as the core screen has bigger distances, the water drains down the screen and eventually it leaves those holes open. That would be an example of how macropores would work in soil, right? So the idea is that water can be applied to the soil, but it will drain out of the macropores into the lower parts of the soil more readily. Whereas the finer screen, where the pore spaces are closer, you'll notice that the water doesn't drain from the screen. It actually stays suspended in the screen because the surface tension of the water is holding it in those tight spaces. So when we're talking about soils and trying to balance the ability to have air and water, we're talking about micropores and macropores. So macropores being where air is kept and micropores where water is kept. So all that plays into soil texture and density and porosity and what makes soil suitable for various crops. Here's a picture of an orange grove, which interestingly enough, oranges really like to grow in sand, which is a very porous soil. So often orange trees have irrigation. I don't know if you can see under here, there is a black line. They use trickle irrigation in orange groves because, of course, sandy soil doesn't hold water very well. And then they have to supplement with fertilizers because sand doesn't store nutrients very well because there's not much clay in it. So interesting though, right? Large pore spaces provide the drainage and oxygen that certain crops need, like oranges. where the clay provides the moisture and the nutrients that crops like grapes would desire. So yeah, sandy soils will dry rapidly after a rain. They definitely have oxygen, but not a lot of moisture content. Where clay soils have very small pore spaces and very good at holding water and nutrients. So there's our grapes. Interestingly, there is an irrigation pipe there as well. That's not common. Certain grapes do need irrigation later in the summer so they don't stress out. But most grapes, their root system goes incredibly deep, so moisture is not a problem for them. So as far as permeability, that's looking at, again, this all sort of sounds repetitious, right? The ease of both air and water to pass into soil, right? So roots can penetrate and access both air and moisture. Clay soils being very low permeability and sandy soils having high permeability. So looking at soil texture, that's in today's exercises, which are outlined on the PDF sheet that's at the top of your folder there. Texture tells us how well the soil could drain or hold water, right? So if the texture tells us that it's a sandy soil, we know it's going to have good drainage. If the texture analysis tells us that it's sticky and holds its form really well, that it's got clay content and it's going to be very good at holding water, which of course it's always a trade-off, right? So if you have good drainage, that means you have good aeration. If you have low drainage, high water holding, that means you've got poor aeration, less air for your roots. Also, if you have good drainage and good aeration, you have poor nutrient retention in the soil because there's low clay content. Whereas in soil that has higher clay content, you've got good water retention, low porosity, less oxygen, but much more nutrient content. So usually we're looking at all the different mixtures of the clay and silt and sand, and that helps us to classify the soil, and we use a texture triangle for that. So on here, you can see on one side, there's our percentage clay content. And over here, we have our percentage silt content. And down here, we have our percentage sand content. So if you can identify at least two of these, which is usually sufficient, trying to measure three kind of gets pointless. You can triangulate where your soil type is. So let's say, for example, we have 20% or 25%. Let's say we got 30%. Let me erase these lines. Let me clear. Let's say you've got 30% clay. Okay, that's up to here. That means we're going like this across here. And let's say we've got 40% silt. So we got to go down to 40. There's 40. Draw our line. And where the two lines intersect, that tells us what kind of soil. We have a clay loam, right? So loam or clay loam, these are the soils that are most commonly found and best for crops to grow on average, let's say. Loam is sort of your classic ideal soil. It's got a good balance of everything. Where the clay loam might be very good for nutrient hungry crops that are also moisture sensitive, right? So, or need more moisture. So what's important to learn from the texture triangle is that looking at the different contents, 40% sand in any soil sample makes it a sandy soil. 40% silt makes it a silty soil. But if you have anything over 20% clay, it is a clay soil. So really want to pay attention to that clay content, right? So anytime you go over 20%, you're into clay-like soils. So if you have a crop that's particularly sensitive to excessive moisture in the root zone, you want to make sure you're at below 20% clay content, right? So sandy loam, loam, silt loam. You don't want to go anywhere over that 20% clay content. In today's lab, if you can go out and find a soil sample, maybe a variety of them, you would moisten some soil and you would attempt to squeeze it into your fingers and form a ball and then squeeze that out to make a flat ribbon. Depending on how the ribbon forms, if it begins to crack and crumble, that tells us that there's some sand content. If it forms a red ribbon easily and doesn't fall apart at all, it's very high clay content. Also, while you're squeezing the ribbon, you can feel the texture if it's gritty or smooth. Typically, you have to moisten your soil sample slightly to get it to sort of become like a doughy consistency for this to work. And so then we look at whether it's a ribbon, if it crumbles, or if it's a partial ribbon, depending on where our clay, sand, or silt content is. Another option is the same sort of idea, and you can do this maybe before you do the ribbon, is just take that soil sample and squeeze it into a ball in your palm. And try to see, does the soil crumble easily after you form a ball? Does it form some structures from your hand, or is palm prints from your palm really visible in the soil? That gives us an indication that there's high clay content and down here, whereas this would be high sand content. In the non-audio version of this ribbon test is a link to assist you in trying to understand how that ribbon test works. So I would encourage you to go out and grab some soil samples and practice assessing if it's a sandy or a clay soil. It's basically, you're looking at the extremes in terms of what sort of soil it is you're looking at. And then once you've decided if it's a clay or a sandy soil, then you just say, okay, is this suitable for what I want? Do I want to amend it? So that's the ribbon test. And there's my final slide, right? So sandy, loamy, clay soils. We'll talk a lot more about this as the term goes on. So if you got more questions, probably going to answer them in another lesson. So I'll show up with a video after this looking at my sedimentation results from my experiment, okay? And otherwise, have a look at the videos where I go over my ribbon tests with the soil samples that I have. One happens to be sandy and the other is clay, so you can see what I'm talking about.